out of practice because I thought I wouldn't be remote again. Oh, it's okay, Jeff. You'll be all right. All right. Now watch this. This is such a cool. Listen. What I'm about to do is a skill that we are going to use several times in this class. So this is a perfect time to do it right now. Some of you have seen this before, and some of you have never seen this before. So here we go. Now let's interpret this question not graphically, but algebraically. This question is asking, when do I have something times something else positive? Yes? When is this positive? That's what it's asking. Yes? So a good question would be, let me ask you this. What's the only way that a polynomial can go from being positive, like if it's positive somewhere over here and I see that it's negative over here, what must have happened in the middle somewhere? So if I see over here it's positive and I see over here it's negative, what must have happened in the middle? What's the only way it could get down there? Can it teleport? What must it have done? Go ahead, Angel.
Asymptote?
Not asymptote. No. I really want you to understand. This is a polynomial, right? You guys have to know polynomials have no asymptotes. They exist everywhere, correct? That's why we gave them the name polynomial. They have no variables on the bottom. They're beautiful. They're nice. They're well-behaved, right? Believe it or not, that's an actual math phrase, well-behaved. We have well-behaved functions, and then we have the asshole functions, right? So we're going to work with some asshole functions. But let me just cut to the chase. Somewhere in the middle, it had to go through the x-axis, yes? That's the only way in hell that a polynomial function could go from positive to negative. Does that make sense, everybody? Okay, all right. Let me see chat going on. Okay, thank you. Now, so what seems to be key, and real quick, if it hits the x-axis, does it have to go from positive to negative? No, it could turn, of course, right? It could turn, yes? How many people remember something called multiplicity from precalculus? Multiplicity? Anybody remember multiplicity? Oh, Chloe, oh, I'm sorry. Does it bring back bad memories? Multiplicity kicks so much ass. I need you to start to love the hell out of it. And I'm going to try to make some connections right now. It's actually also a movie with Michael Keaton. You should look it up. It was not bad. It was kind of funny. Anyway, but that doesn't matter. The Michael Keaton thing doesn't matter. Okay. So here's the idea. Okay, let's do this all the way out. Can somebody tell me now again? This question is about when is this function positive? We just discussed the fact that polynomials only go from positive to negative when there's a zero. That's where they could go from positive to negative. So I need to find the zeros first. When is this function actually equal to zero? That's a nice, easy question now that we've factored it, right? When is this function equal to zero?
3 and -3.
Yeah. So I'm going to put a little 3. I'm going to put a z above them because they are when it's 0. Is that cool? So let me ask you this question. What's the sign of this function when x is 0? When you put a 0 in, what number do you get? I actually don't care about the number. I just care about if it's positive or negative. But tell me, what do you get when you put a 0 in? Just plug a 0 in for x.
Negative.
Yes, good. So I really want this to make all this sense. Has anybody ever seen this kind of diagram before? So if it's negative at 0, it has to be negative at every point between -3 and 3. Yes? Because what's the only place that it can change from negative to positive is when it goes through a 0, when it goes through the x-axis, correct? And what are the only places it could change sign then? -3 and 3. I call those doors sometimes. Those are the doors that let them go through the axis. So in pre-calculus, you should have done like so many graphs. Holy shit, right? When I teach pre-calculus, I call it graphing hell on the first day, just to let them know that the whole point of pre-calculus is to make you graph the shit out of everything. So when you get to calculus, you can make rough sketches very quickly that are still accurate enough. Okay, maybe. Now watch this. What do you get when you put a 4 in, for example? I could use any number out here I want to because it's going to always be the same sign forever after. What do you get when you put a 4 in? I get positive times positive, yes? Specifically, yes. I get 7 times 1, but who gives a shit about the value? I just know that it's positive. What if I put in negative 4 in?
Positive.
Positive. Now here's where multiplicity comes in. Let me ask you this. Did this function change signs on both sides of each 0? Does that question make sense? Like around negative 3 and around, sorry.
It didn't change signs, it remained positive?
No, around
like
the zeros. So from one side to the other of each 0, does it change signs?
Yes.
It's positive here, then it's negative, then it's positive. Yes?
Yes.
Okay. And the reason that is because both of these were to an odd power. They were both raised to a first power. If I raise something to a second power, will it change signs?
No.
Exactly. So for example, if I had x plus 3 squared, right? Isn't negative 3 the 0? Yes? Yes? You're all like, sure, dude, calm down. I'm sorry. And what do I get when I put a negative 2 in? I get positive, of course, because I'm squaring. And what do I get if I put a negative 4? I get positive because I'm squaring, yes? So any even power, the signs will stay the same on both sides. Any odd power, the signs will change on both sides. That kicks so much ass. I'm going to do another example in a minute. Okay. So now we can answer this question. What did the question ask again? The question asked, when is this function positive? Well, now can you just read it off from the number line? When is it positive?
Negative infinity to 3 through to infinity.
Yeah, you could just read it off. You could just see where it's positive. Yeah. Does anyone ever seen that before? No? Okay.
Yeah, I've seen it before.
You've seen it before? Okay. Some of you guys are like, maybe, dude. It might be buried in my memory somewhere. Okay. Oh, let's see. Yes. Okay. Let's do one more example real quick, and then we'll move on. Let me see. I'm going to clear all these away here. I'm going to clear all the drawings away. All my mess of stuff. They're just going to go away. Goodbye. And in fact, I'm going to just open up a new... Oh, let me do this. It's all about me. Aha. Okay. There it is, Jeff. All right, let's see. Can I do it? Yes. Okay, now watch this. Just stay with me, guys. Stay with me. I really want you guys to really just love the shit out of this. Okay. Let's say I have x plus 4 cubed times x minus 2 squared times x. And I want to know, when is that less than or equal to 0? Yes? Can everybody see that problem? Okay. So the way to solve this problem, do you want to graph this, by the way? Do you want to graph this? Anybody want to graph this?
No, thank you.
Okay. And when I say that, I mean by hand, of course. I don't want somebody to go, dude, I'm already, no, by hand. Okay. So let's try to do exactly what we just did, because this again is related to 0. So this is really just asking, when does this function have negative or 0 outputs? When is the output not positive? That's what this is asking. Can you tell me when it's 0? That should be nice and easy. When is this function 0?
Negative 4.
Negative 4.
2.
2.
And 0.
0. I like it. And be really careful. Put them in the right order, right? So I'm going to put a little z above them because that's where it's 0, yeah? So I know those are going to be part of the answer, yes? because it's asking when is it equal to 0 or less than. So I've already got 3 answers. Okay. Now what this is, now watch this. Okay, this kicks so much ass. Do you see how I got 1, 2, 3, 4 regions? I have 4 regions, right? And does everybody really get that the only way I can go from positive to negative or negative to positive is if there is a 0 there? Yes? So I don't care which number. Can somebody give me a number in this region over here? Just give me a number.
5.
Holy shit. Okay, 5. You're good. You're good. Now watch. I don't care what the number is. What do I get when I put a 5 in here? Do I get positive or negative when I put a 5 in this piece?
Positive,
Positive. What do I get when I put a 5 in here?
positive,
Positive. And what do I get when I put a 5 in here?
positive.
Positive. Does anyone not see what just happened? And again, I want to remind you that now is the time to ask, because we're going to do this kind of thing quite a bit later this semester. Okay, so it's positive here. Wesley, what's up? Do you have a question?
I was gonna ask because like for like the X and stuff, like would you not include that with like the little line that not line but the like the little I guess line that you made, like the -4, 0, 2, 5, like would it put that anywhere? Or that's like to the side. That makes sense.
No, I'm sorry.
Wait, okay, so like you said X plus 4, that's -4, and X minus 2, that's 2. So X wouldn't stand for anything?
No, X is where the 0 came from.
Oh, 0. Okay, I thought 0 came from like the 0 on the right side.
No, definitely not. Definitely not. So why did I have a 2? Why did I include 2? Tell me exactly why I included 2.
Because X minus 2 to 0.
Because when X is 2, this piece is 0, yes?
Yeah.
Now watch this. This is crazy. What do I make X so that this is 0?
0.
There you go. There you go. It came. Why is 2 there? The same reason 0 is there, because those values make a piece of this thing 0, which makes the whole thing 0. Yes, maybe. Do you remember the one we just did when it was this? And it looked like this. Do you see how I didn't have 0 there?
Yeah.
Why didn't I have 0 there? Because there's no X piece. 0 does not make the 0. 0 makes this -9, right? So whenever you have an X by itself, 0 will be one of the zeros, because 0 makes X 0, of course. Okay, I really want that, because it's not just you, by the way. That's a really tricky thing for quite a few people. Okay. So I put a plus sign here. Remind me why I put a plus sign there. In fact, I'm going to put a lot of plus signs forever. Yay! Why did we put a plus sign here?
If anything past the 2 is positive.
Good. I like it. Anything past the 2. We used 5, but we could have used 3. Anything on this side will tell me what it is forever. Now, here's the shortcut. Where did 2 come from? It came from the X minus 2 squared, correct? The power is even. So it's got even multiplicity, which means the sign will stay the same. Because, for example, what's 5 minus 2 squared? Positive. What's 1 minus 2 squared? Positive. So isn't it positive on both sides? What about 0? It came from this. What's the power on the X?
Put a 1.
1. So that's an odd power. So around its root, it's going to change signs from positive to negative. And where did the -4 come from?
3.
Something with an odd multiplicity. So again, it's going to change signs around that. Okay, maybe. And if you don't trust me, can somebody give me a number between -4 and 0?
-1.
-1, thank you. I was waiting for some asshole to say -2.7356, Jeff. All right. So -1. So when I put a -1 in, let me erase this here. Go away. Okay. Stay with me now, guys. When I put a -1 in, this would be positive, yes? -1 plus 4, 3 cubed is positive. This would be positive because anything squared is positive. And x, if I put a -1 in, it's negative. So what's positive times negative? Freaking negative, which is what we have here. Yes? Okay, maybe, I don't know. Are you guys okay out there? Okay, maybe. So right now, this is kind of a minor thing, but like I said, later this is going to become something we do quite a bit with. Okay. Anything else about this or from any other things from that first homework assignment?
I have a question actually.
Yeah.
For the question with the toasters, number 22.
Yes.
I had a question. So do we, for the graph, I put the like money as the like independent variable, but then I ended up getting like a negative y-intercept. And I know that like for number C is asking what y represents. Would it be wrong if I said it represented nothing because you can't have like a negative toaster?
Look here. You ready? You look here. Express the cost as a function of number of toaster ovens, right? So the cost is a function of, I don't know what you want to use for that. Let's not use T because it looks like, let's use N for number of toaster ovens. Cost is a function of the number of toaster ovens. So my number of toaster ovens is like my X variable, and my cost is like my Y variable.
Oh, okay.
So they didn't tell you like directly. They just sort of hit it in the first part. So when they give us this, does everybody see on number 22, they give you 2 points? Anybody? They give you 2 points that this graph goes through. Does anyone agree with me? That's what they do. What's 1 point they give you?
Like 1,000, 9,000, or
yeah, the input is number of toasters and the output is money. Money. There you go. Angel had the universal sign for money. There you go. So that will help you out a lot because now your slope is going to be a lot better than it was to begin with. And you're going to get an actual intercept that makes physical sense. Yes.
I got you. Thank you.
You're welcome. All right, guys. Anything else? Because real quick, do you guys remember what's happening on Monday? There you go. Chloe's got you. Quiz. Quiz just on chapter 1. And that's why I made the homework due. When did I make the homework? Yeah, I made the homework due Sunday night so that I can actually, Sunday night or Monday morning, I can look at it if you turn it in. Now, again, real quick, just to remind you guys, I didn't say this before, and this is my fault. I put the due dates in Canvas for now, just to be really clear what your goal should be. Homework still won't be counted late if you give it to me by the day of the test. But I am desperately trying to put you in the right mindset. Don't freaking do it the night before the test for a couple reasons. One, you'll suck on the quiz, right? If you don't do any practice, you're going to suck on the quiz. And two, because if you try to do the entire homework set before the test, you're not going to. And then you're going to suck on the test, and that's really bad. Okay. Anything else from that first homework assignment? Okay. How about any chapter 2 questions? Anybody sneak into chapter 2? I know a few people have. Okay, all right. So let's do this. Oh, by the way, we have a quiz, and I'm still, to be really honest, all right, I haven't decided exactly how to do it yet, which is really bad for me, but it's just too bad. I could do the quiz at the beginning of class with everybody here, And everybody's, well, actually, to be honest, I don't even need everybody's camera on necessarily in that case. Or I could make it a timed quiz that would be due. I normally give at least 24 hours to do it, but it's timed. Does that make sense? So the minute you open it, your timer starts. So you don't really have 24 hours to do it, but you have 24 hours to find time to do it. Yes? Yeah, I think I'm leaning towards doing it the second way also, because that would give us more lecture time too. The quiz wouldn't take away any lecture time. Okay. If there's no really huge backlash against doing that, I think we will do a timed quiz, and you have time to kind of figure out when you can do it. Does everybody understand what's happening? And just to let you know ahead of time, in this case, everybody, not everybody, good Lord, but there will be several different versions of the quiz, right? You don't necessarily get the same version as somebody else. So be really careful about, being in each other's house and sort of doing it together, because you might not have the same quiz. Ricardo, yeah, just chapter one. And I might as well say right now that I'm planning on a week from next Monday having a quiz on 2.1 through 2.3. So you might as well write that down. Sure. Sure. I'm here once again to tell you that the quiz. Sorry. You say that and I think of Bernie. Okay. Anything else before I get back into where we left off at chapter 2? Okay, good. So let me erase this stuff from yesterday, or you know what I mean, yesterday. Get over there. Let's see if I can make this work. Boop, boop, boop. Go away. Okay. Is this a good lighting situation? I think so. Yikes. There might be too much light. No, maybe that's all right. No, that's good, right? You guys are good. Okay. All right, that's my phone. Let's see. So real quick, I want to kind of go back. Exactly, Tom. Can somebody help me out? I haven't really told you the full way to say this. Now, just to read this, you would say the limit as x goes to a of f of x is L. L is a number. Are you guys with me? So visually, this could be something like that. Is everybody with me? Yes? Okay. Now, if I ask you, what does this mean? Not just how to read it, but what does this mean, right? So this is kind of huge. What this means is we can make the outputs, good Lord, Jeff, of f of x arbitrarily close to L by making the inputs, let me see, by using inputs sufficiently close to A. Get out of there. So if the limit at A of f of x is L, then I have to get close to L as I get close to A. If I didn't, then it isn't the freaking limit, right? So does that just kind of intuitively make sense that if that really is the limit, then if somebody wants me to be really close to it, I just have to get close to A, and then I can get close to it. I can get as close to it as somebody wants me to get. Now, one little thing, let me change one little thing. Would anything I've just said change if this was an open circle?
Oh,
Good. No. Because what's the one thing the limit doesn't say anything about? This limit says nothing about what?
Including or excluding?
No. This limit says nothing about what is happening at A. Really, this is where people really lose the idea of limit. This limit, this statement, says nothing about what is happening at A. It only says what's happening as we get close to A. Yes? So what could be happening at A? It could have an open circle, like a pothole, I like to call it. It's a pothole. Does that look better? No, sorry. Yeah. So there could be a pothole at A. The function could actually kind of momentarily transport somewhere else. Yes? We can do that with mathematics. It's kind of hard for us to do it so far yet, like Star Trek. But mathematics, bam, I just did it. Ha ha. So the limit doesn't give a shit. In fact, not the limit doesn't give a shit. It just doesn't care. Well, same thing, Jeff. I don't allow it to get to A. That's the whole idea of a limit. And that's why they're so useful for investigating weird places, because we don't go to the weirdness. We just get really close and go, whoa, right? Okay, maybe. Okay. So let me ask you this. Let me see if everybody remembers this. I'm going to erase all this. I'm also going to destroy my eraser. Well, that's different. Aw, poor little dude. Wait a minute. Okay, I think he's all right. I'm going to erase all this. Are you going to be okay? We'll find out. It's okay so far. Gonna be okay? All right. Yeah. So tell me, answer me this. So here's f of x. Yeehaw. Let me see, how does it look for you? Yes, okay. I like it. 1, 2, 3. Weehaw. What is the limit as x goes to A? Let me put a little, you could do it, Jeff, little negative sign there. Somebody remember what that means? What that would be?
portrait from the left.
Yes. Now, I want to apologize right now, just to let you know. I might sometimes say from below, and that is unfortunate. It's just the way I was taught. I'm going to say that. But from below always makes it seem like I'm Jaws coming up. Blah, blah, blah. Look at that, man. I'm already. Well, anyway, so blah, blah, blah. But it does mean my inputs come from below, right? So my inputs come from the left. What does it look like the function is doing as I use inputs approaching A from this direction? What is my function doing as I get closer and closer to A?
It's getting close to 3.
Yes, the outputs are getting closer to 3 as my inputs get closer to A. So here I am, my output's there. Here I am, my output's there. So the outputs are getting closer to 3 as my inputs are getting closer to A from this side. What about this, of course? Somebody else tell me this. And that's fine, okay. Gotcha. Sorry, guys. Anybody have this one? What's the answer to this one? So it's the same situation, but now I'm letting the inputs go to A from that direction. So as my inputs come in from this direction, what are my outputs doing as you get closer and closer and closer to A? What are they going to? What are the outputs going to?
1.
Getting
1.
closer to 1.
Yes. Cool. Now, in either of those situations, did it matter where the open circle or the closed circle was? Did that matter with either of these answers? Because you guys see where the closed circle is, right? You guys see the open circle, correct? If I would have switched those, would anything have changed here?
No.
Not a damn thing would have changed, because again, I don't give a shit. The limit doesn't give a shit about what's actually happening at A. I really need you to get this. And that's why I can use it to investigate things where weird shit happens at a point, happens at an input. What is f of A, just out of curiosity? What is f of A?
Impermanent?
Nope.
F of A is 1.
F of A is 1, because that's where the closed circle is. Bam!
Oh, my bad.
And again, this fact has nothing to do with these. Now, can somebody tell me, can I give this an answer? Is there an answer to this question?
No, because the left and the right hand limits aren't the same.
There it is, Jeff. You can point there. Yeah, these two are not the same. Therefore, so for example, if I ask, if I'm like on the phone with a friend and I'm like, okay, I'm coming. Okay, me too. I'll see you in a minute. Okay, all right, I'm here. So am I. Do we agree with where we are? No, obviously not. It's like, where are you? No, thank you for that. I like that. Now I'm gonna want everybody to make a little no, yes, little sign. So what we would say here is does not exist. That limit does not exist. Okay, I like it. Okay, cool. I like it. So like Wednesday, we discussed some general things about limits. Now I'm going to come back in with some more details just to fill it in a little bit. Now, any questions on this idea? This is really important. Okay. Oh, Jeff, you are dying, you poor little dude. I'm going to make you work for a minute. Do I have another eraser? No. Okay. Yes. Yeah, let's look at this. So real quick. All right, this is going to be a little annoying, but it's too bad. Oh, let's make, it doesn't really matter, does it? Yes, it does. Okay. This is a problem we looked at yesterday, and let me see, this is not really coming through for you guys. Let me get this over. There we go. How do we investigate this? How did we investigate this Wednesday? This kind of thing. What did we do? Does anyone remember? Is it really that long ago? Every day is like a month now, Jeff. I know. So what did we do 2 months ago when we did this kind of problem? What did we create? And I showed you how to do it in the calculator to make it quicker.
A table.
I like it. So the way I like to do it, you don't have to do it the way I do it because the book does it a little bit differently, but the way I like to do it is I know I want to get to 0. So I could say like 0.1, 0.01, 0.001. And then from below or from the left, I could do negative 0.1, negative 0.01, negative 0.001. So then I can see what does it look like it's approaching. Yes? All right, I'm going to need some help real quick. Where's my calculator? Oh. No. There we go. Okay. All right. Any way you want to do it. Oh shit, my poor little battery. Come on, you can do it. Any way you want to do it. Can you make this table? You want to do it that way, Jeff? Yes, I do. Okay. Hopefully everybody's working on making this table. instead of just waiting for me to do it. Oh yeah, you get somewhere really quickly. I should have probably picked a little bit. Anyway, does anyone know this here? When you put a 0.1 in, what do you get?
0.2498.
In there. Yes, Jeff. 0.2498. All right, somebody else tell me this next one.
0.25.
0.25. So, and the next one is 0.25. So we pretty much got there pretty quickly, right? We didn't have to get too close. So on the other side, you get 0.2498 also, and 0.25. So this is not a difficult guess to make. What do you guys guess the limit is?
0.25.
0.25, yes. So I would guess that this limit, my guess is it's 0.25. Could the answer actually be 0.2500000003? Yes, as far as what we've done, it totally could be, because we're not, but that's a pretty damn good guess. It looks like it's zeroed in pretty well. Now, I'm gonna kind of leapfrog some stuff and then come back to it. I since this is up here, oh shit. So reminder. Does anyone remember? Good Lord, Joe. What am I drinking? Let me have some more of it. Whoa, okay. Does anyone remember how to simplify something like this here? For example.
Turn it into exponential form?
Nope.
You rationalize the denominator.
True. How? You just
I'm multiplying rad2 plus rad5.
yes, good. And it doesn't matter what the name is, but does somebody remember what the name of that was?
Was it the conjugate?
Good. Because when you do this, that's 2, and then you get positives, root 10 minus roots, all the radical shit leaves, minus 5. So the bottom becomes a nice rational number, which is why we call rationalizing, because we make it rational. It's crazy. Okay. All right, I don't care about that problem. So watch this. Oh, man. I mean, there's my eraser. Yay. All right, see if I can make it work for a minute. Poor little dude. I'll just step on you for a minute. There we go. Move back. Now, here's something that's really kind of strange. Can I do that same thing here? But what piece of this needs rationalizing? The top, yes? What's the conjugate of the top? What would I multiply top and bottom by?
The square root of x squared plus 4 plus 2.
Yeah, that's all the conjugate is change the sign. So top and bottom. Now, why would you do this? I don't know. Let's find out what happens. Let's see what happens, right? On the bottom, I'm just going to keep this as x squared times, oops, don't be doing that, times stuff. But what do I get on the top? What is rad x squared plus 4 times rad x squared plus 4?
X squared plus 4.
Yeah, that's the beautiful thing. Half of this times the other half is a whole this. And then I get plus 2 of these, minus 2 of these, middle terms cancel, minus 4. So what happens to the top there? I just get these cancel, yes? And then these cancel, yes? So I get 1 over square root of x squared plus 4 plus 2. Now, let me ask you this. Is this expression, is it the same as this expression? You could do it. There's sort of a right answer and then a more right answer. I want the right answer first. I want the surface level. This is the same as that. This is the same as that, except at 0. Because what did we just, that's where this thing has a problem, correct? So why is that? So this guy has a problem at 0, but this is legal to do. And when I do this, I'm not changing the function. It's the same function. So this function does this everywhere except at 0. So that's why I'm allowed to do this. That's why the answer for the limit will be the same if I do the limit of this, which we did here, or if I do the limit of this, which is easy now. Do I have to do any craziness here? Can I just plug a 0 in and get an answer?
Yep,
What do I get? Yeah.
you get 0.25.
Yeah, you get 0 plus 4 is 4, square root of 4 is 2, plus 2 is 4. I get 1/4, which is 0.25. Isn't that nice? Because aren't you already getting tired of making tables like this? Even if you haven't done it in the homework yet, aren't you kind of tired even with just a few? No, you're not. I love it. Angel, that is the actual right answer. You're like, oh, I could do this all day. Little Captain America math dude. I could do it all day. I like it. Okay. I don't know. This poor little dude. Okay. Now, so that was a lot. We just, this kind of thing, you're going to see a lot of this in chapter 2. You're going to see the conjugate kind of come up. Okay. All right. What about, all right, here's something exceptionally funky. Oh, I love this little dude. Of course I would. Let's do this one first. All right, this is not exceptionally funky. This is pretty straightforward. It still has a little bit of funk to it. It's got a little bit of funk, but it's not exceptionally funky. Think about this for a moment here. Is sine x approaching a value as I let the inputs get large? What is sine doing forever? What does sine do forever?
In forever, it hits 1 and -1.
And everything in between, right? So forever,
Yeah.
sine is just doing this. It's doing this forever. So if I move down this x-axis to 80 billion, it's still doing this. If I move down the x-axis to 80 billion to the billion to the billionth 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 power, which is a number that's way beyond anybody's comprehension, it's still doing this, yes? So is the function approaching a value as I let the inputs get big?
Oh,
No. In fact, it's not. So the answer here is does not exist. Sort of like the same reason the answer didn't exist when it was this. Is the function internally consistent? Does it agree with itself? No. If this is kind of like a different way, but is it agreeing on any output as the, no, it's not agreeing. It's like -1, 1, -1, 1, -1, 1. I don't know. All right. So this is what is called an oscillatory discontinuity. It's oscillatory does not exist kind of thing. It just does not go to a value. Now, I love you guys so much. I really hope you're with me because, okay. Now watch this. Does anyone see any similarities between this one and this one, besides the fact they both have a sign?
X can't be 0.
True, but what does 1 over x go towards as x goes to 0?
the different values, no?
Yeah, true. That's a good point. So let me do this. Let me change this just a little bit, just to make sure that you might be getting an idea perfectly right. Let me do this. Did that too much on it? So as x gets smaller, what happens to 1 over x squared? As x gets really
It
small.
approaches zero.
Say again, sorry.
It approaches zero.
No, definitely not. The bottom approaches 0. Sure. As x gets small, x squared approaches 0. But what does 1 over x squared do then?
It gets bigger.
Gets bigger, of course. 1 divided by 0.1 is 10. 1 divided by 0.01 is 100. Holy shit. Yes? Is that cool? Yes. So do you see how these are really the same question? Anybody? What are the inputs doing in this one? The inputs of sine, what are they doing? They're getting really freaking big. They're getting really big. Yes? I'm letting them go to infinity. I'm letting the inputs get really big. What am I letting the inputs do here? I'm letting the inputs get really big. Yes? So this is the same answer for the exact same reason. In fact, watch this. This is kind of sucky because I put the square there, but you're okay, Jeff. It's fine. So what is this thing going to look like? If you try to graph this, what it's going to look like is something like, I don't know exactly, it's going to look something like this. I think I might have this backwards. Oh, well, I think it's going to look probably like this. If you try to graph this thing. So I don't know if anybody tried to graph. So what's and here it gets insane. So I don't know if anybody is interested or will understand, but what this does is infinity is normally off the picture. Yes, infinity is normally off the picture. Does everybody agree with me? You're like, yeah, Jeff, yeah, we get that. Infinity's like forever that way. This makes infinity happen right here. Because when does this become infinite? At 0. Yes? Yes? So this kind of takes and smushes, it smushes this from infinity. It smushes it all to be right there. All right, you've gone way too far, Jeff. Bring it back in. I'm really sorry. Hopefully you got a little bit out of that. This is a little more than you have to be able to do right now. Oh, I just see somebody just left. Damn it. They're all like, this shit. Okay. But I love, it's just so neat to me to bring something we can't see and just bring it all right here. This is infinite oscillations here. Okay, that's enough, Jeff. That's enough. That's enough. Take this away. All right. That was a little crazy side note. Oh, let's do this. What's the difference between... Is there a difference between these two things? I kind of gave it away a minute ago. I kind of gave this away a minute ago. Let's see if anybody...
There's no difference between them. One just happens faster than the other.
Okay. Your second statement is correct. First statement, there is a difference between these two for sure. What does this symbol by itself mean? Doesn't it mean it has to happen from the left and from the right? Yes? This symbol by itself, there's no plus or minus here, correct? I really want you to remember, guys, what the only way that a limit can exist at an input is if it agrees from both directions. Do you remember? We had that one that kind of jumped and they didn't agree. So how could we say there's a limit because they don't even agree? So watch this. What happens when you put negative values? What happens to this if you come at 0 from the left? It'd be like 1 over negative 0.1. That's negative 10. 1 over negative 0.01. That's negative 100. 1 over negative 0.001. That's negative 1,000. What is that going to? Negative 10, negative 100, negative 1,000, negative 10,000, negative billion.
Negative infinity.
Negative infinity. And of course, what happens if I put in stuff on the right? Then that's positive infinity. So what is the limit as x goes to 0 of this period? Does not exist, because this is the most disagreement you can have. I think it's negative. I think it's infinity. That is about as far apart as you could be. Yes? Negative infinity. In fact, what does this thing look like? You guys remember this? Doesn't it look like this? Do these agree at 0? They disagree the most you could disagree, right? Okay. Maybe. Okay. So like if I follow this and you follow that, do we end up at the same place? We end up at the most far apart place possible. What about this guy? Do you guys see the difference now? If I do it from below or above, if I put negative numbers in here, doesn't the square just make them positive? So what is this limit here? If I put negative numbers in, it just becomes positive anyway, because I'm squaring, correct? So what is that limit?
Positive infinity.
Positive infinity. And of course, this one will also definitely be positive infinity. So how can I write this answer then? Do they agree? Do those limits agree? Do these agree?
Yes.
Yes.
Yes. I like Angel, that's awesome. So this answer is positive infinity. Now, just to really make sure, infinity is a form of not existing. Infinity is kind of like the limit doesn't exist, but if they agree on what kind of infinity, you must put that as the answer. The only time you could put does not exist is if they actually disagree. Is everybody with me a bit? This is all very new, should be pretty new for most of you guys, but it's sort of stuff you talked about a little bit in pre-calculus. Okay, maybe, depending on your teacher. What do you want to do next? Sure. How much time you got? Okay. And real quick. Can anybody tell me what that answer would be? Without too much thought, based on what we just did.
That's supposed to be a 5 or an S?
It doesn't really matter, but it's supposed to be a 5.
Oh, okay.
I'll try, I'm sorry. Please.
Does not exist.
Exactly. And just in general, if I write something you can't read it, tell me. I know I have. 3s are my worst enemy. 5s suck for me. Basically, letters and numbers are the only 2 places I have issues are with letters and numbers. Yeah, this does not exist for exactly the same reason that the 1 over x didn't exist. Above 4, it's positive. Below 4, it's negative. So it goes to negative infinity, positive infinity. Okay. Bye. Yeah, okay. So we basically just finished up section 2.2. I'm going to try to start being better about putting what section I'm in. Section 2.3 is an exceptionally, just to be really blunt, very boring section. So I'm sorry. It just is. It sets up all the laws of limits. Can somebody? All right. Let me ask you this. Side question. Sidebar. Can somebody tell me what they think the limit as x goes to 2? What's the limit as x goes to 2 of x squared minus x? Can anybody tell me what their gut tells them that
2.
limit is? Say again?
2.
How did you get that?
Just plug in 2 for the x's.
Just plug it 2. Because when do I need to make a table is when I can't actually just plug the thing in. This function exists at 2. And it agrees from both sides at 2 because it's polynomial, right? You guys, so it's a well-behaved function. So I don't have to do a table. I don't have to do any reasoning about left and right. It's a well-behaved function. I just throw 2 in. So yeah, I get 4 minus 2 is 2. Wow, right? Okay, maybe. So that's why if plugging 2 in ends up with something that is indeterminate, then I've got to do some more work. I've got to make a table, or I've got to do conjugate stuff like we did it a minute ago if I'm going to do it algebraically. Okay. So the limit laws, let me erase this. Dadgummit. Do I have a different eraser? I guess I do. It's called paper towels. Okay. So real quick. Limit law number 1. The limit as x goes to a of f of x plus g of x is the limit as x goes to a of f plus the limit as x goes to a of g, which is basically what we just did, except I had a minus sign. In fact, to save time, I'm just going to put a freaking plus or minus, plus or minus. Okay, right. So that's something that we've kind of done intuitively a couple of times already. So let me ask you this real quick. Well, no, I got a better, yeah. Let's see, if I have enough time, I'm going to show you something out of the book. What's the next one, Jeff? Oh, really? Okay. The limit as x goes to a of a constant times a function believe it or not, this will just be the constant times the limit of the function. So, I mean, for example, just a real quick little example. What's the limit as x goes to 2 of x minus 1?
1.
1. What's the limit as x goes to 2 of 77.3 times x minus 1?
77.3.
Yes, because I could, this little dude, it doesn't matter. I'm going to plug a 2. I'm going to get this limit. I'm going to get this limit, and then I'm going to multiply it by this stupid number, right? That's all that's all that limit law is saying. And it's kind of like, I got that limit law, right? So I'm hoping that some of these are sort of very basic, but limits are new things, and we have to establish how they work. And they definitely work exactly the way we wish they would. Okay. So that equals 77.3. I'm going to put that, and then I'm going to erase it immediately. Okay. What else you got, Jeff? Yeah. Boom, boom, boom. What do you think the limit as x goes to a of f of x times g of x? What do you think that might be?
The limit of f of x times limit of g of x.
Crazy sauce. All right. We've basically already done this. So for example, what's the limit as x goes to 1 of x squared times x minus 1? Sure, why not? So don't I have a function times another function? Yes. So what's the limit as x goes to 1 of x squared?
It's 0, right? It's just kind of hard to see
yeah.
because of the glare on the whiteboard.
Oh, is it? Oh shit, you're right. Oh well, okay. So I don't know. I can't really make it any better with that, can I? No. Poor little. Oh, there you go. Oh, it's you. It's you. It's always been you. Oh, it's this, is it? It's that. Okay, it's my screen. Okay. So this will be x squared. Let me see. There you go. If I stay here, there it is. This will be 1 times 0, which of course is 0, which is really what this is saying. Okay. Yeah, that's the third one. What time we got? What are you gonna do here, Jeff? Yeah, the fourth one, remarkably enough, the fourth one deals with division. The limit of this is equal to the limit of. So the limit of a quotient is the quotient of the limits. Can anybody tell me where there might be a problem with this? When would this expression have a problem?
The limit of as x approaches s of g of x equals 0.
Yes. So this is true if that limit is not 0. That's kind of obvious, yes? Bottom can't be 0. We're screwed if that's true. Okay. Let me see. Blah, blah, blah. Okay. Oh my God. Let me just throw these other ones down here real quick. What this is doing for us, by the way, is it's telling us what kind of functions can we just throw inputs into to figure out the limits. So here's a couple of really nice ones to know. The limit as x goes to a. What's the next one, Jeff? Yes. Of a function being raised to a power is the limit of the function being raised to that power. We've actually already done this when I had x squared and we plugged a 1 in. It's the same thing. Same thing works for nth roots of something. You can just take the limit and put it inside is basically what this is saying. Oh my God. Okay. Can somebody tell me what is the limit as x goes to a of 7?
Seven.
Oh, I see. That one's you. Okay. I'm gonna have to work on that. Yeah, this is 7. This is kind of crazy. As x does anything, this is just 7. It's just sitting there being 7. So it's like x, you could do your weird shit. I'm just always 7, right? So that's kind of silly. Any constant, the answer will be that constant. That should make sense. Okay, and the other ones are kind of more. Okay. Yeah, I don't know if I want to. Yeah, maybe we can. Let me do this. Let me try to show you. As I sit down, I'm going to try to remember what it was in the book I was going to show you. What was it? Maybe I won't because I can't remember right now. Okay. I'm going to erase a couple of these real quick. And then we're going to do something exceptionally strange. What was it, Jeff? I got to remember. It's all right. All right. I think I think this will be enough for today. This will be the last thing we do today because it is kind of a freaky idea. So let me ask you something. What if I had, let's start off nice. Okay, first level. First level is a nice level. What if f of x is always less than or equal to g of x, except maybe at x equals a? So f, the outputs for f are always less than or equal to the outputs for g everywhere, except maybe at a. At a, it could do anything because guess what? What would the limit as x goes to a? How would these relate, of course? How should these relate? Are they equal to each other? Is this one bigger? So if the function f is always and forever less than or equal to g, right? So the function f is always and forever. Those are two different colors and they both show up. Do you guys see the two different colors there? Oh, well. And I'm curious about some point, doesn't really matter, a. I don't care where I pick a to be. What's always true about the limits? Obviously, it's got to be less than or equal to. It's so obvious. My marker is like, you don't even have to write that shit, Jeff. All right. Does that make sense? I mean, that's kind of silly, right? If all the outputs for a function are less than or equal to some other function, then the limit at some point must be. Why does it not matter at A? Watch this. At A, this could be true right there for F. F could go bam. Does that change this idea at all? I really, this is the weirdest part of this. What's the limit as x approaches A of f of x? Isn't it this? Isn't that the limit? Does it matter that at A is up here? Why does it not matter what happens at A for this question here? Why does it not?
Because f of x is still less than or equal to g.
No. At A, isn't f bigger than g? Right there. At A, isn't f above g? Because do you see how it's an open circle and it goes up there? Does everybody see that? So at A, f is bigger than g. Oh shit. Why does that not change this statement at all? What is it about limits?
It's never going to touch A.
Good. The limit never lets the input equal A. So that's the underlying thing about limits is they cannot say anything about and therefore don't give a shit about what is happening at that value. This is so weird. I know. But it's also freaking cool as shit. Okay. Now, here comes the weird part. That was not the weird part. Let me see what you guys think about this. This is where I should probably use the book's pictures, but you'll notice that I'm not. Okay. What if I had a situation where f of x is less than or equal to g of x is less than or equal to h of x for all x except maybe x equals a? So what does this mean? This means that here's f of x. Whee! Oh, let me yeah. Let me add one more thing. Yeah, Jeff. Slow your roll there, buddy. Slow your roll. Come back. Let me also say that the limit as x approaches a of f of x equals the limit as x approaches a of h of x equals some number L. Oh, crap. Stay with me now. So G is always between F and H, and the limit at A of F and H they equal each other. So what does this look like? How can you screw this picture up, Jeff? Let's find it. Let me put A down here just to make this. So here is F. Yeehaw. Okay. And here is H. You see if this shows up as a different color. So H has to be above or equal to F. So it could do this. But the limit as it goes to A must be the same as the limit as F going to A. Okay. And then you've got, oh man, are you guys still with me? Are you guys are like, you lost me at hello. Okay. And then here is, so I should really identify these. This is H. This is the topmost one, right? The biggest one. This is F. And then here comes G. G's always got to be in between. Yes? Aw. Can you even see that? No. All right. You've picked the worst spot to do this in, Jeff. All right, I'm going to put you guys down. There you go. Now there won't be too much. Okay. Oh, is it this one? Yeah. Can you guys see that? Yeah, you can see that. It's always got to be in the middle. So what has to happen to g of x as x goes to a? What must be true? What does the limit of g have to be? If it's always between these two, What happens at A? The ceiling and the floor come together, yes? Maybe? No? You guys hate this?
So then g of x has to also equal L.
Careful, be really careful. I don't know what is happening at A. It could all be open circles here. So it's not g of x equals L, it's the limit of as x goes to A of g of x has to also be L. Now you're gonna love this. So I really want that to make sense. If a function that's always bigger than me and another function that's always smaller than me, both hit something, I have to hit that same thing also. Not I gotta be careful with my language. Not hit it, but at least approach that same value. I have to approach that same value. I've got nowhere else to go. I've got to agree with them at that point. My limit has to agree, because where the hell else am I gonna go? Okay, I know you guys love this. Everybody always loves this. Not quite the same way I do. Now watch this. What would you call this theorem if you had to come up with a name for this theorem that where I've got the floor and the ceiling kind of smushing me? Smush.
Squeeze theorem.
Squeeze theorem, yeah. That is the official name of this theorem, squeeze theorem. Okay. Okay. Maybe okay. I could squeeze in. Yeah, Jeff. No pun intended. Look at me. I'm all okay. Let me. I'm sorry. Let me squeeze in one example of this. Right. Let's do a concrete example. Wouldn't that be nice for a change? Let's do a concrete example of this. So what if I had the limit as x goes to 0 of x squared times sine of 1 over x. Now I cannot just plug a 0 in, because what did we determine about this earlier? Do you guys remember? What's true about this?
It goes on forever. Oh, wait, no.
So what is, not it goes on, what's the answer to the limit of that piece? We did that one earlier.
Oh, DNE.
Does not exist. So I can't just plug a 0 in to figure out what this is, because that doesn't even exist. So now watch this. This is so weird. Can anybody tell me that piece, isn't it bounded? I don't care how weird the inside of a sine or a cosine gets. I don't care what sits inside them. What's true about their outputs? What's the smallest output sine can have, and what's the biggest output sine can have?
-1 and 1.
Yes. You really have to divorce. It doesn't matter what's inside. All the weird shit that's inside doesn't do a damn thing to the outputs. The outputs can only be -1 to 1 unless I change the amplitude, right? So it's be -1 to 1. Is that the function that I'm curious about? No. What do I do to make this show up in the middle? Don't I multiply everything by x squared? Don't I have my correct function in the middle now? Yes? Isn't that like my g now? This is my g, here's my f of x, here's my h of x, this is the floor, this is the ceiling, and this is us in the middle. Stuck in the middle. Now watch. If I take the limit as x goes to 0 of everything, what's the limit as x goes to 0 of -x squared? That should be easy. What happens when you let x go to 0 for x squared?
0.
0. What's the limit as x goes to 0 of positive x squared?
0.
0. So look what this says. This says the limit of x squared sine 1 over x is at least 0 and at most 0. So what's the only thing it can be? If it's at least 0 and at most 0. Isn't that what that says? So what?
0.
Yeah, the limit of this is 0. And if you graph it, now real quick, here's x squared, yes? Here's negative x squared, yes? You could do this. If I were you, I would try to graph this on your graphing calculator because it's so cool. Let me see. So if I do this, look what happens. Here's the sine function coming in. This effectively acts as the amplitude. So that's not a constant amplitude. The amplitude is getting bigger on either side and it's getting to 0 in the middle. This is a really bad picture and I apologize. You should do it on your calculator just to get a better picture, but I think they might actually have it in the book too. Okay, but I think that is enough for today. If you want to hang out for a second, I'm going to go ahead and do it on the graphing calculator, but you only have to stay if you want to see it real quick. Otherwise, you're free to go. If you have other questions, hang out. If you want to see this, let me do it real quick. Sorry. I love this kind of thing. It makes me think, anybody out there playing music?
Yeah,
What do you play, Brianna?
I play violin, viola, piano, guitar.
And what's really nice about the violin, after you've plucked a string, isn't it nice that eventually it goes away, the sound? Can you imagine if that just kept going forever? So every guitar or violin we've ever plucked is still going. The human race would be insane. So thankfully, the oscillations are dampened, so they eventually go away. So this is what reminds me of that. So if I do x squared times sine of 1 divided by x, I don't know what kind of weird ass scale I'm on here. Oh, Jesus. Oh, I am in radians. So what have I done incorrectly? I've done something horribly wrong. Oh, that's right. Jeff, you're crazy. I didn't even put in my floor, and then I put my function in. By the way, my picture's really wrong because I forgot it's 1 over x. It's not just sine. And then my ceiling, x squared. All right. So this is not quite what I had, but it's too bad. Let me just because I want to, I'm going to change this to be sine of x. Oh, Jeff, you crazy person. There we go. That's kind of like what I was trying to do up here. I forgot that the input was 1 over x, not x. But this is kind of nifty. It kind of lives between the ceiling and the floor here, and then it gets smushed in the middle. That's squeeze theorem. Okay, guys. Let me know if you have any questions. Otherwise, I will see you Monday. Don't forget quiz coming.
We didn't get to see it.
Oh, Jesus. I wasn't even sharing my screen. I'm sorry. There. I'm sorry, Ricardo. Somebody, I wish you would have spoke up earlier. Like, what is he talking about? Okay. Take care, guys.
I have a question real quick.
Yeah.
So this is really basic and I'm very sorry. But can you quickly explain when we did limit of x approaches to 2 of x plus 1, why that was 1? Just so it's solid in my brain.
Yeah, sure. All right, let me clear this.
And then the same thing for when limit x approaches 0, x squared, why that was 0.
Oh, here. So what was the first one you said again?
Limit, it was x approaches 2, and then it was x plus 1.
X plus 1?
Yeah.
I think it was x minus 1, but okay, x plus
Okay.
1 is going to be.
It might have been. It could be wrong in my notes.
But I want you to see what we did to investigate limits that had a problem at the input was we made a table of values.
Mm-hmm.
There's no reason to make a table of values because does this have a problem at 2?
No.
No. So if I just plug a 2 in, I know exactly what the limit is. So the graph of x plus 1 doesn't have any freaky things happening. So if I want to know what the limit is as x goes to 2, I could just plug 2 in.
Oh, okay, got
Yeah,
it.
so then I get 2 plus 1 is 3. Now, I really want you to understand. So when do I really have to make a table? Well, what if I had this?
Oh, yeah.
Right?
Mhm.
This is 0 over 0, which is indeterminate. And earlier I was thinking about trying to shove this example in, but let me really make sure you get this. What if it was just this? This is not indeterminate.
Mhm.
I don't have to do any more work. I don't have to make a table because I could tell when it goes to 2 from the right, it goes to positive infinity, right? Because the closer x
Mhm.
gets to 2, the smaller the bottom gets. And when it goes to 2 from the left, it goes to negative infinity. So this does not exist. This one, when I get 0 over 0, shit. The reason we call it indeterminate is because I cannot determine the answer directly from what I'm looking at. Right? This one I can determine directly, very directly. This one I can determine directly, not as directly, but I can think about it for a second and get it. This one, oh shit, we got to make a table of values, or I got to do some other funky stuff. Yeah.
Yeah.
Okay.
All right, sounds good. Thank you. Have
Welcome.
Thank you.
a good
Welcome.
weekend.
You too.
Right, I have a question.
Yeah.
Or you were doing like a problem where like you were saying that it didn't matter that the f of x of a point was like all the way on the top. I still understand like why doesn't it matter?
Oh, because in that situation, so let's say this is g of x, and my f of x, I think in that case the f of x was always smaller or equal to it, right? So and then we have this
Yeah.
a. So it was like f of x is less than or equal to g of x. So what's true about the limit as x goes to a versus the limit as of f versus the limit of g, right? So if f is always below g, except maybe at a, right? Because that's the way I set it up. At x equal to a, it could do
Yeah.
whatever it wants to. So at x equal to a, f of a could actually be way the shit up there, right? You with me?
Yeah.
Now, can you tell me, let me try to give some numbers here. I don't know. 1, 2. What's the limit as x goes to a of f of x? Does this have anything to do with that question? What's the limit as x goes to a?
It's gonna be like 1 or a little bit below 1.
Yeah, something around 1, right? Especially with my crappy drawing. And what's the limit as x goes to a of g?
2.
2. So this is still true. It's still less than, it has to be less than or equal to, because f is always below g, except maybe at a. But does the limit care what happens at a?
No. Okay,
No.
so because
So
it's like looking at the function as it approaches a.
all it cares about is where does it look like it's going, not where does it get to, but where does it look like it's going. So that's what the limit asks. So f looks like it's going to a value that is less than what g looks like it's going to.
If I like let's say you arbitrarily like move the a like 10 more points to the right, would that mean that like f of x doesn't have a limit then because it like oscillates too much? Or how does that work? Like how would you be able to tell if it oscillated like that highly
I
and
don't
then came back
understand
down?
wait. I don't understand what you mean by move a and oscillate.
So like I guess like let's say you move the limit like to the right. Like the
make
point
sure
A, where point A.
All right, move this somewhere. Is that what you mean?
Yeah, like to the right basically. Yeah. Then would you even be able to get a limit for f of x? Because like it comes
Here.
to the top.
Just move it here.
Yeah.
So then this doesn't mean shit
Yeah.
to me right now. Now, if I move that there, does that actually agree with what needs to happen? Is F always less than G except at A? No, because now F is bigger than G at some point.
Oh,
So
okay.
the way I've
I
set
got
this
you.
up is F has to be less than G, except maybe at the point we're interested in the limit at.
Okay.
I see what you mean now. Although if
Okay,
I
I
move
think
that, then I've changed the one place F can do funky shit. So F is
Yeah.
not allowed to do funky shit
Alright.
except at A. I like it. Okay, and this is, like, trust me, limits are weird, but the main thing about limits, they don't care. They can't care what's happening at the input, right? At A. They don't know. They don't care. They don't. The actual output could be anywhere, and it doesn't change anything the limit thinks about. I really want
Okay.
that to be.
All right. I think I understand.
Real quick, just go with me for a second. So, what's the limit as x goes to A? It's 2, right? Oh, dadgummit. I keep pushing
Yeah.
the wrong. All right. This pen is driving me crazy. All right. It would be 2. There it is. What if I put f of A there? Isn't the limit still 2?
It would still be, yeah, it would still be 2.
What if I put the limit there? Would it still be 2? I mean, not the limit, but the
It would still
function
be
value.
2.
What if I put the, what about
Yeah.
right there? Oh, well, it's still, the limit is still 2. It doesn't matter where the function output is because the limit doesn't even let me get to A. So I don't know what's happening at A. I don't care what's happening at A when I am the limit, right?
I have a question.
Yeah.
Just kind of like, it's a little bit unrelated, but still related. But with like the sine and cosine function, you said that like it oscillates too much for there to be like a limit, or like the limit doesn't exist from both sides because it oscillates too much.
Yes.
Like, is there like a threshold for like how much a function cannot oscillate before like there's a limit?
So let me say this. I was going to say this after I talked about the dampened stuff. If I had, now watch this, it's kind of cool. If I had some, now watch this. Let me put this in here. So this is like 1 over x, not 1 over x. I don't care what that is. This is like, screw it. I need to be more careful when I make this, but let me see if you get this. So here's an oscillate. It's oscillating forever. Yes.
Yeah.
You see how it has to live between these? So if this is approaching 0 and this is approaching 0, then this is also approaching 0 because the amount that it's oscillating is getting smaller and smaller and smaller. So it is approaching 0. Yes, just from both sides.
Yeah.
But if I just have a natural sine function, it's always going to be. So if I think the limit is 0, it gets away from 0 at some point. If I think the limit is 1, it gets away from 1. If I think the limit is -1, it gets away from -1. It never kind of homes in on something. So that's why it's
and never
when I think about when x gets really big, is it getting close to something forever? No, it's anything it gets far away from it, and then it gets close to it again, and then it gets far away from it. I really want this to make sense. So for the limit to exist, so like a horizontal asymptote idea, is this function getting closer to 3? Yes.
Yeah.
What about this function? Is it getting closer to 3?
Well, yeah,
Yes,
because eventually
because the amplitude is getting smaller and smaller. But what about, what if obviously the next thing I'm going to do is, what about this? Is that getting closer to 3? No.
No.
It never gets close to 3. It's just always bouncing around. It never agrees that it's going to be 3 forever. This looks like it's agreeing to become 3. This looks like it's agreeing to become 3. This is like, I don't know. Yeah.
I got you. Okay.
Okay.
All right, then I think I got it. I think I'm gonna get this homework done then.
Sweet. All right, man.
All right, thank you.
See you Monday. Bye, everybody.